Hi, I'm Bob from Hauptwerk Hardware, and in this video we're going to take a look at this. It's the main System 1 control board, and it sits between the computer running your virtual organ software and the interfaces inside your console, which are connected to the console's various controls, such as stops, pistons, keyboards, etc. System 1 is a MIDI organ control system specifically designed for use with organs. It can handle up to 120 motorized stops, 128 lighted stops, 128 lighted pistons, as well as other ancillary items, and it also includes a power management system which allows you to control your virtual organ computer from the console's on-off switch in a controlled way, so that everything is saved and the computer shuts down simply by switching off the switch on the console. So let's get this thing on the bench and have a closer look at how we can use it and what it does. We've got the control board on the bench now so that we can take a closer look at it. So there are basically two sides to this board from a logical perspective. One side connects to your computer, which is running the virtual organ software, and the other side of it connects to the various interface boards that you install in your console to connect to your keyboards and other controls. So basically there are a number of connections on here that go to your computer. There are two MIDI interfaces. One's a USB MIDI interface and the other one is a 5-pin DIN interface. And the reason for having the two is that the keyboards and pedals all send their MIDI out of this port here. And everything else on the organ sends and receives its MIDI through this port here. And the idea of keeping them separate is that there will be no interference between the MIDI controlling everything versus the MIDI coming from the keyboards. So what we don't want to happen, for example, and I've had people mention this with other products before now, is that the latency between pressing a key on your keyboard and the virtual organ software responding increases if there's other MIDI activity going on at the same time, especially when if you're halfway through quite a fast piece or that. From a musical perspective anyway, at a point where you want to change registrations, you hit a thumb piston, which is then going to select quite a large registration. You may have 20 or 30 motorized stops that need to be changed in their position. And then obviously the light on the piston needs to change to the one you've pressed. And that actually takes quite a lot of MIDI events to do that. And if all of those MIDI events are coming down the same interface as the MIDI stream that's coming from your keyboards as you play, then obviously the computers are very, very fast, but there are limits to what they can do in a certain amount of time. So if you get quite a lot of MIDI information in a burst like that, it can cause some latency. So the thinking behind this is we have two completely separate processors. This one does all of the keyboards and the pedals, and this one does everything else. This interface is connected to this processor, and this processor has its own USB MIDI interface. So that's the thinking behind that. And then over here we have another USB connection, and this is just a serial port. So you can plug this into your computer, and you can use a terminal program such as Putty, which we've used with other products from Hauptwerk Hardware. And this will show you exactly what is happening with the control side of this board. So in other words, if you've got this connected to a terminal and you pull a stop, for example, or you press a piston, you will see the terminal will come up with a print to say that you've pulled that particular stop, and it's sent a MIDI note on event, on channel, whatever it may be, for note number, whatever it may be, for the stop that you've pulled. And likewise, if you push that stop back. Also, if it receives a MIDI message through this interface here, to activate or deactivate a stop, then it will print that on the screen as well. So you can see exactly what's going on, what's going in and out of this thing from a real-time perspective of what this controller is doing without having to worry too much about trying to decode the MIDI. Because whilst you can do that, I mean, you don't have to use this port at all. You can just plug this into your PC or Mac or whatever you're using, and you can use a MIDI monitor program. And so when you pull a stop, it's going to send obviously the MIDI to the computer, and that's going to show on your MIDI monitor that channel 10, note 25 for argument's sake, has been sent as a note on. And the reverse happens obviously if you change the stop back to where it came from. But that requires that the MIDI is plugged in and working, and it also requires that you can remember what every stop is likely to send, and it can all get a bit messy, really, to be honest. So it's just much easier to plug into here and use a serial monitor, and you can see in more human language exactly what's happened when you pull a stop or you operate a piston or something like that. So I just think that makes it a lot easier. You don't really need to know what the MIDI codes are coming out of this, because this is going to plug into your computer. You're going to be running your virtual organ software on the computer, and most of the time you're going to be able to say to your virtual organ software, okay, auto detect what this control is doing, and it will, because it's going to see the MIDI and it's going to say, oh, okay, then that was whatever control you've told it to auto detect, and it'll just map the two together. You don't need to know what the MIDI MIDI commands are. So this makes that a lot easier, in my view. So that's what that's there for. So those really are the three things that connect to your computer. So you've got USB MIDI for your keyboards, you've got DIN MIDI for everything else, and you've got serial so that you can monitor what's going on when you're setting this thing up. I don't suggest, by the way, that you leave this connected once you've finished setting everything up and it's all working, because obviously it also takes time to print stuff out on the screen. And so this will significantly slow things down, and you don't really want that to happen, and you don't need it to happen, because obviously when you're playing music you're not looking at a terminal screen. So that's really just for setting up. So then we move on to the other connections on this board. So we've got these two connectors here. All of these connectors, if I tilt that up, you can see are just ordinary RJ45 Ethernet Cat5 type connections. Obviously they're not carrying Ethernet, they're carrying the various signals to the various interfaces which you will have in your console, but they use exactly the same cables and plugs, which makes it very, very easy to connect everything together, because you can get those RJ45 or Ethernet cables made online to anything you want. They're very cheap, they're very available, and it just seems the obvious way to do everything to me. So there are two here for keyboards. Now, if I can almost get that into the light correctly there so we can see it, the bottom one just above the socket, hopefully you can see it says Matrix KB, and the one up here says Bus KB. So that means that if you've got a keyboard that's wired up in a bus configuration, you would use a bus keyboard interface, or interfaces if there's more than one of them, and you would plug those into this socket. And that's pretty much all you've got to do. There's no setting up required with that. The board will recognize that you've plugged in however many, 1, 2, 3, 4, however many keyboards you've plugged in, because you can daisy chain these things together. And I'll show you that when we get on to the video which deals specifically with the bus keyboard and the Matrix keyboard interfaces. So that's what this one's for, first of all. And then this one is obviously, as we've said, is for Matrix configured keyboards, and you can mix them as well. So you could have maybe your 2 or 3 manuals, maybe of a matrix configuration, and they'd be plugged into this socket here. And then your pedals might be a bus configuration, and they'd be plugged into that socket there. And this will just figure all that out. You don't need to program anything, that just works. And you can have up to 7 keyboards in total. So 6 manuals plus pedals. And I'd be surprised really if anyone wants to go any bigger than that. So that's what this is capable of. And that all comes, as I say, from this interface. So we can kind of think of it as that's all for our manuals and pedals, and everything else is for everything else. And everything else being motorized stops, because you've got interfaces, optional interfaces that you buy or you fit in your console dependent on the features or the specification of your console. So if you've got motorized stops, you buy a motorized stop interface and you plug it into here. You can have up to 120 motorized stops, as I said earlier on, and the interfaces available are 24 and 48, I think. Can't actually remember now, believe it or not. But you can daisy chain these together as well, and I'll show you those when I do the video on the motorized stop interfaces. But you can have up to 120 motorized stops. Again, no programming or anything. The more you plug in, this will just realize or see that you've got them plugged in, and it will just control them accordingly. And then lighted stops is pretty much the same, apart from you can have 128 lighted stops. You're limited to 120 motorized stops, but you can have up to 128 lighted stops. And then on this socket here, we've got our lighted pistons, and the same applies with that. We have a lighted piston controller. There are a number of those available for different configurations of pistons, and they come in a 32 and a 64 piston version. So you could have a 64 piston version plugged into a 32 piston version, and that's going to give you hopefully the number that you need. If you need more, obviously you just buy more interfaces or the bigger ones and you plug those together, and then that plugs into here. And then on the end here you've got another socket which is labeled as aux board, and this is for the auxiliary board, and this controls things like the there's a twin 7-segment display board available, which is used to indicate the capture system memory level or user number level, whatever you want to call it. Also, it gives you another 8 inputs which you can use for anything not previously covered, really. If you've got some other switches on your console that do something, say maybe a transposer or anything really, you can connect those to the auxiliary board. And as well as that, the auxiliary board gives you up to 40 outputs that you can drive LEDs with. So if you need to have a say a crescendo level or crescendo step indicator, for example, that's where you would use the auxiliary board. If you had 6 or 10 LEDs from lowest to highest, that would all be driven from the auxiliary board, and that just plugs into here. So that's pretty much how all that works. Now, along the back edge here, we've got our analog inputs. So what I shall do is I'm going to zoom the camera in a little bit here, just so that we can see, hopefully, a little bit more clearly along the back here. So we've got these inputs here. They're labeled A1 through A8, and they are exactly the same in the way that these little pins are configured as on the Tutty encoder, and the same as our swell pedal encoder. So if you've got anything already wired up, if you're upgrading, say, from either of those, then you can literally just plug these in. And if you're not upgrading, you're just starting afresh, then you've got 3 pins here. One of them is plus 5 volts. The middle one is our sense pin, or our sensor pin, whatever you want to call it. But the middle one is the one that's going to vary between 0 and 5 volts. And that's what's going to give you the control change value between 0 and 128, or 127, actually. and the bottom one is 0 volts. So really, you just take your potentiometer effectively and plonk that across there, and that will just work. Again, there's no programming required. You don't have to tell it that you're using these inputs or anything like that. As soon as you start using them, it will just generate the necessary MIDI, and it will send that out of this interface to your computer. So that takes care of your analog interfaces. I say there's 8 of those. And then moving across here, we've got 4 kind of blank sections. These are for future use. They're not actually used at the moment, but they're for expansion as more features get added to this. And as I also mentioned, I think in the introduction video I did on System 1, if there's anything else that this doesn't already do that you can think of that you would like it to do, that would be a useful feature for you to have in your organ, then pop it in the comments below so that I can look at continually improving this to include more and more things so that everything's covered for what everybody wants, hopefully. Obviously, it's never going to be all things to all people, but we'll try our best to get close to that. Then we've got these 4 jumpers here, and those are LS polarity, so that's lighted stops polarity. And what that means is that the lighted stops are usually arranged in a diode matrix. And the way this works, it actually uses a 16:2 matrix to give us the 32 different state inputs, if you like. So it's on and off for 16 lighted stops. But we'll get into all of that when I do the video on the lighted stop interfaces. But it's based around the ubiquitous lighted stop boards that you kind of find on lots of different organs. Anyway, dependent on which way round the diodes are on those boards, depends on which position you would put this jumper in. So it needs to know that. And then we've got LP polarity, that's lighted pistons polarity. That's exactly the same thing. It's just which way round the diodes are on your lighted pistons, if it uses a matrix. If they're bus type lighted pistons, then this next one, the yellow one, LP mode, is lighted piston mode. And this, in this position, selects lighted pistons wired in a bus fashion and using a bus lighted piston interface. And in the rear position, it selects the matrix interface and matrix wiring mode for your lighted pistons. And then the last one here, marked up as 7-seg. That's for if you're using the 7-segment display along with the auxiliary board, which you'd have plugged in here. So if you are, you put this in the rear position, and if you're not using the display, you put it in the front position. The reason that it needs to know this is because there are 40 outputs for LEDs on the auxiliary board, and when you use the 7-segment display, the first 16 of those are reserved, if you want, for the 7-segment display. So if you want to use all 40, you need to have that in the other position. That takes care of those. And then moving along here, we've got our power connectors here. So VCC is 5 volts and ground obviously is 0 volts, and you would connect those accordingly. Whilst you could rely on the USB lead here from the computer to supply the power to this whole thing, bear in mind that this board is then supplying power out to all the other boards, and it's much better and much more reliable if you use proper power supply here. So that's why we've got 4 pads. They're just connected together, so 4 VCC pads, 4 ground pads. You can easily connect those off to your various parts of the power supply. Then we have 3 more connections here marked relay, which connect to the relay. And we've got common in the middle, normally closed on the right and normally open on the left. Now, what that's about is for remote control switching for amplifier systems, really. If you've got a headless organ and it's installed in a venue or something in a church, and you've got a bank of amplifiers that run speakers in the church, you don't really want to have those amplifiers on when your virtual organ is booting up. And the reason is, as I'm sure you're aware, if you listen through your speakers, if you put the speakers on before you put the organ on, you get all sorts of pops and bangs and strange noises as the sound drivers are loaded and various other things happen. So the idea is that when your organ is ready to play, when you've finished, when everything's loaded and it's booted up, you program your organ to send a MIDI signal to here. And when this board receives that MIDI signal, it will then activate this relay, which will close these contacts and open these contacts. So you can use that to then control the power to the amplifiers. Normally, there's just like a 12-volt control cable or wire included in the loom off to the amplifiers, a bit like they do with those big amplifiers for cars. When you've got the radio switch on the dashboard, you switch that on, it supplies 12 volts to a kind of control pin, if you like, on the amplifier. It doesn't control the actual power going to the amplifier, so that's important to remember. This is just for remote control. It's not for switching the actual power to the amplifiers. So just bear that in mind. This is fine for 12 volts. They're dry contacts, so there's no power on them at all. But I wouldn't go above kind of 12 or 24 volts on here, because you don't want to start mixing high voltages with all the other things that are going on inside your organ. So that's what that's for. And then finally, we've got these two connections here. One says ready and the other one's PWR state. So PWR state is power state. That connects to, via our little power management board, and that connects to the on-off switch on your organ console. And it's a soft on-off switch, so it's not really controlling any power. It's simply switching voltage level to this pin. This is used, as I say, in conjunction with our little power management board. And the idea is, normally we have a bicolor LED, a red and green LED, and we have the power switch which connects to that. And when you first power the organ up by switching this thing on, it will control via an ATX power supply. All of this is designed to work with an ATX power supply, the power management part of it, that is, and along with the power. But it will switch on or enable, whatever you want to call it, the soft control pin, trying to get the right terminology here, but anyway, to the ATX power supply. So obviously once that has been powered, that will switch on and start booting up your computer, and it will also light up via our little power management board the bicolor LED in a red condition. And then, as we said earlier, when we were talking about controlling this, once the computer has finished loading everything and booting up and so on, you get it to send a MIDI signal to this. When this receives this MIDI signal, it will operate this relay, as we said, but it will also put a high signal, if you like, a high level signal on this ready pin. And our power management board will respond to that by turning the red LED, the bicolor LED, green, so that the user knows that the organ is now ready to play. And likewise, the power state, when you switch the switch off on the console, power state will see that. It will send a shutdown signal back out of these. Well, it's just a MIDI signal, but you configure it in your virtual organ to be shut down, which will then obviously save any registrations, close the software virtual organ application, and then go ahead and shut down the main computer. And then when the computer's finished and it's actually shut down, the LED, we've got our bicolor LED, as soon as it sees this power state change and it knows the shutdown process has begun, that will turn back to red. And then when the computer's finished shutting down and it switched itself off, obviously the power's removed, so that LED will go out. So that's kind of in a nutshell how the power management part works. But I'll show you all of that in another video when we start looking at the power management. I've got a couple of interfaces connected up to the control board now, just so that we can take a quick look at the sort of output that we get on the computer. And on the computer, I've got a terminal on the left here, which is connected up to our serial port here. And on the right hand side is our MIDI monitor, which is MIDI aux, and that is connected to this output here. So MIDI aux is going to be monitoring the MIDI coming from our keyboards, and the PuTTY session on the left here, that terminal, is going to be monitoring what we're doing with this interface over here. This is a lighted piston interface, a matrix lighted piston interface for 64 lighted pistons. So basically it's got two matrices, and there are 32 LED outputs for matrix A, 32 LED outputs for matrix B, and then we've got 8 rows by 4 column inputs for matrix B, and 8 rows by 4 column inputs for matrix A. So what we can do then, let's just simulate something going on. So first of all, if we simulate the keyboard, this is a bus keyboard interface. So it's got actually 64 inputs. Normally on your keyboard you'd have 61. These are all labeled with their note names, so starts at C1 at this end and goes C sharp 1D, D sharp and so on, as you'd expect, all the way up to C6 here, which is our 61st input, and then there are 3 spare ones, and then there's just a ground connection at the end there. So these 3, if you've got just 1 or 2 pistons or something, thumb pistons, other switches, whatever it might be in the vicinity of your keyboards, you can just connect those to here, which saves on having to get a whole separate interface for just 1 or 2 pistons. So if you had 2 manuals, for example, because of this, that would give you capacity for 6 inputs over and above what you're already using. So the downside is, yes, the MIDI is going to come out of your keyboard MIDI. However, for some pistons that are only sending MIDI, because they can't operate lighted pistons or anything like that, these are just inputs, that's not going to make any difference, not going to slow anything down. So that's absolutely fine. So just gives you a bit more versatility. So the way this usually works, with a bus keyboard, you have one bus running along the back of the entire keyboard, and that bus is connected to plus volts. So we're going to simulate that with this test lead here. So we're just going to touch that onto one of the plus volt pins on this board, and then the other end of this lead I can touch to the inputs. So if I touch that to C1, you'll see on the monitor on the screen that we get that C note on event. If I let go of it, you get note off and so on, and if I run that up the keyboard, you can see those note on offs obviously go up as you'd expect. Now you don't get anything from the serial monitor when we're operating the keyboards, because as we said, they're completely separate processors. We don't want any interference with what's going on with the keyboard, so the keyboards just send MIDI and that's it. They just work. But with the other side of it, we can see exactly what's happening by using our serial monitor there. So if I take this matrix, for example, if I go column 1 to row 1, if I touch that on there and release it, you can see on the serial terminal here, that's sent a note 32 on channel 9. So it's a note on, note 32 channel 9, and a note off 32 channel 9 when I released it. So then if I went to say number 8, we now get a note 39 on, note 39 off, and so on, and that's basically how that works. Okay, I've plugged in a MIDI interface to this port now, just so that we can have a quick look at what happens on the computer when we send some MIDI to this. So this is our serial session over on the left here, which is coming from this port here. And on the right, we have this Pocket MIDI application, which allows us to send MIDI as well as to receive it. So what we're actually doing here now is that if I operate this matrix piston as I did before, so if I connect column 1 to pin 1 on and off, so you can see on the screen here we've got note 32 on and note 32 off, and then in the MIDI monitor here you can see it's all in hexadecimal, but basically those are the MIDI bytes that say note on is that one for note 32 and note off. So that's what happened there. Now also if I send some MIDI, so by pressing the keyboard keys here, the virtual keyboard on here, that will send MIDI to our board, to our control board. So if I operate this key, for example here, that sends note 0 on, and you can see that it's come up and off when I let go, but you can see that that's come up here on our serial monitor. So when I pressed note 0, we got a lit piston 0 on. When I released it, we got lit piston 0 off. And obviously if I press a different note, you'll get different numbers as you work up the keyboard, as you would expect. So that just shows us what we're getting out of this thing. But also I think that's why this is quite useful to have this serial monitor, because you can see exactly what's being received. You know what's supposed to be happening. For example, there where it says lit piston 29 on, obviously when you see that received, then lit piston number 29 should light up, and if it doesn't, then you know exactly where you've got to be looking between output number 29 here on our actually I think we use this matrix, so it'll be that 29 on our matrix piston controller. So you can check obviously that you've got power there. If it says that lit piston 29 is on, then there should be 5 volts here. And if your piston isn't lighting up, this just makes it nice and easy, because if you didn't have this serial monitor, then you wouldn't know if perhaps the MIDI hadn't been received by the board, or if the board hadn't decoded it correctly, or if something else was going on. Perhaps it had been, you know, received here, but there's something wrong with the connection to this. Obviously, in which case you wouldn't have the green light. But anyway, you get the idea. I think this is quite useful. So that's basically it. I'm not going to go through and connect all the other sorts of interfaces for the moment. We'll look at those individually in the upcoming videos. So we're going to do a different video for each type of interface, not each variant necessarily, because there are different variants of these things. For example, the lighted pistons, there's a high voltage version and there's a regular 5-volt version. And likewise for various other kind of variants of interfaces. But we'll look at what the variants are, and we'll try out certainly the low voltage variants with this board as we go forward making those other videos. So that's it really. That's just an overview of what the main board does, what it's capable of, how you connect it up, how you use it. As I said, if there's anything it doesn't do that I haven't mentioned that you would like it to do, then put a comment. Please leave a comment below so that I can look at those, and you know, we can hopefully improve this thing together in time. But other than that, I think that's probably about it for this video. So I'll put a link below to the System 1 document. There's a System 1 overview or introduction to System 1, I think it's called, document on the website, which is very comprehensive. It explains all of what I've said about here and more about these interfaces. I'll put a link to that below. I'll also put a link to the first video in this series, which was just the introduction to System 1. And the next video on System 1 is going to be on these bus keyboard interfaces. So we'll look at what we can do with those and how we can, you know, what the options are. We've got this polarity jumper down here. We can daisy chain them together, and we'll look at what happens when we do that. So that's it for now. Thanks very much for watching, and I'll see you in the next video.